Now you might have to, maybe the easiest thing would be if you all just move down and then the students can sit at the end then, yeah? Okay. Dude, you're so antisocial. Keep going. Okay. Yeah. These are good things to consider, yes. How many classes over? Right. Have I got everybody? No, Speedway, do I?
Speedway, yeah.
Yeah, do you know where she is? I mean, have you seen her today?
Yes.
She is in? Yeah, okay. So next page now, page 72. Okay. Okay, we're good. Now, you should remember from near the start of the semester, when you have a quadratic equation, you know how to find this point. Do you remember what you can use to find this point? Completing the square. But so far, we haven't learned how to find it for cubics or other shapes. Does anybody remember the name of this shape? This point? Turning point, and there's another name as well. Minimum, yeah. Turning point, minimum or maximum. Anything else? Critical, very good. Critical point. That's not really one I use though, I'll just put a line through it. No, but it's fine. Anything else? One that begins with a V? Vertex. And one new word, maybe this one is new, it begins with an S. Stationary point. So the two common words, well, these would be common names for them. Stationary point or turning point. Okay. That must be Speedway, so. Everybody likes. Now what we can do, I can just use the desk, but we'll make an extra table. I hope that's not going to be too close. You should still be able to see. Yeah. Vicky, move your feet. I think you'll be okay there. Did you have a piece? Okay. So what was I saying? Stationary point and turning point. So let's see how we can find them. So let's have a look at our graph for a cubic. So here is the tangent here, and the slope of this tangent is called what? What's the name for the slope of the tangent?
Gradient.
The gradient, or the begins with a D. That's what you did last time. Derivative, yeah. So the derivative here is positive. What about here? It's negative. But at the top, if I draw the tangent line, what's the derivative here? 0. And here? 0. So you notice on graphs, at turn-in points, the derivative should equal 0. And actually, this is the key to this lesson for finding the turning point. So please note this. This is the key idea for this lesson. That to find the turning point, you need to find when the derivative is 0. Yep. Can I do an example? Yes? Let's pick an example where we can do it by completing the square. So for example, if I have x squared plus 4x plus 10. Here, if I complete the square, I get x plus 2 squared plus 6. Yeah. Yeah. And if I draw it, I get this kind of shape. What is the minimum point here? Minus 2 and 6. Let's use the new formula from today to see if we get the same answer. Of course, we should get the same answer. This would be embarrassing if we don't get the same answer. So, this is like method 1, the old method. Now let's have a look at the new method. So, we calculate the derivative. What's the derivative here? 2x plus 4. And we want to know, when will the derivative equal 0? Well, that's when x equals, if I solve this, what do I get for x? Take the, minus 4 over 2, which is minus 2. If I take this and put it back in here, I can get the y. And I'll find out that the y is 6. So the answer in this method is minus 2, 6. Which you can see is the same as the first method. So my point is that this equals 0 works. We can use this to find the turning point. However, this has many advantages. What's one big advantage of using this method?
It's not like...
Yeah?
It's very easy.
It's easy? I mean,
this is
easy to do, isn't it? Yeah, not many steps. What else is another advantage?
Let's work with the cubic.
Yeah, no, this is the biggest advantage. Question, Leon? Yeah? No, you can ask me. Is there a question? It's okay? So the biggest advantage is that this works for quadratics, cubics, everything. Whereas complete the square only works for quadratics. Okay? So let's do an example now with a cubic. Okay? So first write this one down. So this is like the older method and this is the newer method. But they both give the same answer. Have you got this? Will we do a cubic now? Okay. So if you picture the shape of the cubic, how many turning points should there be?
2.
There should be 2, a maximum and a minimum. Okay. Y equals 2x cubed minus 18x squared plus 50, this is messy writing, minus 18x squared plus 54x plus 30. Okay, first step, derivative. dy dx equals, what do I do? 6x squared minus 36x plus 54. And you want to know when will this equal 0 to find the turning point. Well, divide by 6. What have I got here? 9, isn't it? Yeah, it's okay. This has this has one factor. Okay. So the turning point could have 2, but sometimes it could have 1. Depends on the shape of the cubic. Yeah. So this is x minus 3, x minus 3. So the turning point is when x equals 3. I can put that back in to get the y. Two times 3 cubed minus 18 times 3 squared plus 54 times 3 plus 30, 84. So the turning point is 384. Now you might wonder, oh, if there's only one turning point, then the shape is not like this. If there's only one turning point, the cubic looks more like this. So where do you think the turning point is on this graph? There, is it? Right, exactly there. Yeah. The turning point is right here, because if you draw a tangent line here, this is where it's flat. Okay, so I know this is maybe a weird example to do first, but if I draw the graph for you, so this cubic doesn't really have the usual up, down, up shape, because this cubic only has one root, so it's a little bit strange. But anyways, the turning point here is not always a maximum and a minimum, okay? So usually the turning point is at the top of a max or at the bottom as a min. But in this example, the turning point is right about, I don't know, about here. What was my exact value? 3, yeah. So that would put the turning point here. And if you think about it, that makes sense, because if you look at the graph, the slope here is 0. It's quite flat. Okay? So we use turning point. Turning point is more general. Minimum, maximum doesn't work here because there is no minimum, maximum. Turning point is where the slope is 0. And here is where the slope is 0. Okay. We'll do another cubic. Hopefully this cubic has 2.
Second derivative.
Yeah. Oh, that's later. Oh, no. Oh, that's later. I won't say anything about that yet. It gets more complicated. And this has a special name as well. Do you remember it?
What?
Begins with an S.
Oh,
It's something you put on a horse.
Saddle.
Very good, yeah. Saddle point, yeah. But that's a different lesson. For today, it's just turning points. Okay. Can everybody try this one before I do it? So, I want the turning points for this cubic. Can everybody try this before I do it? So I want everybody to get the turning point or points. Got it? Yep. So, firstly, derivative, that's 6x squared plus 42x plus 72 equals 0. I think we can divide by 6 because this will be x squared plus 7x plus 12 equals 0. Now, does this have roots 4 and x plus 4 and x plus 3? Yeah. So 3 and 4 are the roots, are the factors, x plus 3, x plus 4. So we have x equals minus 4 or x equals minus 3. And then we put these values back in here to get the y's. Did somebody do this already? Or, yeah, what's this y? Minus 8? 68? And then here? Minus 69. Okay. Let's have a look at the graph here. Okay, 2x cubed plus 21x squared plus 72x plus 12. Okay, let me try and get this a bit better zoomed in. Let me just move it down a bit. That did nothing. Okay. I suppose it's hard for me to get the up-down part, but I hope you can just about see. This is kind of like the hill part. I think I can do much better than that. Right, now the problem is I can't see my axis. Well, that's nicer. So whatever x value is here, this is probably the minus 4, and then this one here is the minus 3. And the height here, the minus 4 height is somewhere between 65 and 70, and then the minus 3 height is closer to the minus 70. So I think that matches up with what we got, a minus 68 and a minus 69. This one on the right is a little bit lower down than the one on the left, but there's not much of a difference in their heights. This is only one higher than this one here. Look at that. No, wrong. Right, so this one is minus 4 and minus 68, and this one here is minus 3 and minus 69, which you can not see the 3 and 4 here, but they're there. Okay, let's clear that. Okay, so this one here, minus 4, minus 68, and this one here, minus 3, minus 69. So do you remember when we were making the cubic graphs, we learned how we know where it crosses the y-axis, that's easy. And we also learned how to find the roots. Now from today's lesson, we also know how to find the turning points. We already knew how to find that. What's this one called? The blue one. Y-intercept. So now we have the intercepts, and we have the roots. And from today's lesson, we have the stationary point or the turning point. So do you remember there was a cubic graph we were trying to do at the end of the lesson? And it was a little bit difficult to do because we only had like 1 point, and we weren't sure if the graph, I can't remember, we had a choice, the graph could go, I can't even remember, the graph was either going to go like this or, I can't remember what it was, But if you looked at your notebooks or the video, we weren't sure which shape it was. But if we knew the turning point, we could draw it because I think our choices. What were they? It was something like
It comes from down, yeah, and goes up, cross the x-axis,
cross the axis,
goes down.
down, and then goes back up.
Yeah.
Or that was it. Or it could. What is it? What was the other one? It could go up, down, and up like that, was it? Yeah, that doesn't help. Thanks. I think my choices were we were either thinking it was like this, or the other choice it could be.
Because we like at that time we only know the roots and
Yeah, that was it. We had one route, and we weren't sure if it was like this,
yeah.
or if it could have been like this. And I think there was another choice as well. I don't remember. Anyways, these both have only one route. But if you knew the turning point, you would know which one to draw.
The other one is in the positive way. After it crosses the y-axis.
After it crosses the y-axis. Start here.
Yeah.
Up.
Cross the x-axis and y-axis. Go straight.
Just go straight.
Yeah.
Just like this.
No. Now it goes down.
Yeah.
And goes
Oh yes, it was maybe it turns after the y-axis, wasn't it?
Yeah.
Like it was something like it turns later.
Your choice was this one. Yeah. That's
Yeah. Oh yeah. Turns before the axis, under the axis, or after the axis, whatever. I don't even remember. But my point is, if you knew where the turning point was, if you knew the turning point was up here, here, or down here, it would make drawing it a lot easier. This is the point I'm making. Anyways, let me give you another one to try. Power 16, yeah. What should you do first with logs? You should simplify it before you start. So what can you do with the 16? Bring it down, yeah. Okay, try this. Impossible. You got it, Tony? Is it impossible? Do you have an answer? You should have an answer. Good. You got x and y? Get y also. Got an x and a y? Yeah? Okay, I see some people finished, which means they got it or they gave up. Gave up? That's okay. It's okay, yeah. Alright, let's have a look here. So, before I start, I should change this into 16 log x minus x squared minus 16x minus 2. Now I calculate the derivative. What will this be?
16 over x.
Minus 16 equals 0. Now, I should point out, of course, that x is not allowed to be 0 because we have a log here. So it is okay to multiply everything by x. Now, wait, please, this is very important. I'm multiplying everything by x here. And I can only do that because I know x cannot be 0. So I multiply everything by x here. And I divide everything by 2. And I take to the right. And I get this. Now this has two ugly answers.
Yes.
Very ugly.
This is point 8.9
Hang on.
and minus 8.9.
Well, I'll tell you right now. So the first one is 0.89898, and then the second one is minus 8.89898. And we can put these in to get the y values. Has anybody done that?
Minus
For the first one, minus 18.
Yeah, 0.89. Actually, is it okay if
That's fine, yeah.
0.9? I think
That's okay. And what about this one? The minus 8. Do we have that? Minus 8.89898 power 16 minus 8.89898 squared minus 16 times minus 8.89898 minus 2. So here I got 96.17. So my first one is 0.89898 minus 18.89. That's nicer. My first one is 0.89898 and minus 18.89. And my second turning point is minus 8.89898, 96.17. Is that right for the first one, minus 18.89? Did anyone else get that?
Yeah, this is
You got the second one the same as me? Yeah. Do I need to reject any of these answers? So if you look here at my x answers here, Do I need to reject any of them? What do we think? Accept both?
I'm not sure about the minus one.
We're not sure about the minus one. Why not? Why can't we use minus?
Because when we differentiate and
Well, that too, yeah, but maybe a bit more back at the start of the question, though.
but you have 16 is
Exactly. We can use minus because the power 16 here in the log makes everything positive. So the x can be negative here. It just can't be 0. Because of the power 16, it just can't be 0. Yep. Let's have a look at this graph now. So just write that answer down if you didn't get it, and we'll make the graph here. So before I draw this graph, we have 2 turning points. So what type of shape are you picturing? Maybe it's like a cubic because it has 2 turning points. It goes up, maybe it goes back down. Let's have a look at it. It's not going to be cubic though. Can you read it out? What is it? Log x power 16. Yeah.
can you remind us what graph of the log?
Graph the log, it increases. Right, you're looking at me. So for you, it looks like this. It increases to the right. Okay, so the graph here. Let's reset. Now I know the values are quite big on the y-axis, so I'll need to go down. And what were our 2 x values? Were they small? Yeah, okay, so let's see what we get. Okay. Oh yeah. So what was the positive x value? It was 0.89 and minus 18. So there's 0.89 and there's minus 18 about, or well, it's around about here. So this is kind of like a maximum.
But they are 2 different graphs.
Well, they're just 2 totally different shapes. What was the other point? Minus 8. Now I don't have minus 8 here. I need to zoom out. Now. Minus 8, what was the value? It was 96. So you can see there's minus 8 and there's about 96. So this is the maximum, this is a maximum, and here's another maximum. So this graph has, it's like a McDonald's M shape, it has 2 maximums. But you might think, oh, I missed a point. What? It looks like I missed what? It looks like I missed a minimum, doesn't it? At 0? Yeah. So, yeah, well let's have a look, let's zoom in here.
There is no value at 0.
Yeah, but it looks like on the graph there is. So let's see what happens. Now I know there isn't one at 0, but on the graph it looks like there's one at 0. So we need to see what's happening here. So if I zoom in, so the minimum looks like it's minus 60 here, doesn't it? So let's zoom in a bit more. Yeah, it is. Minus 70. Okay, let's zoom in a bit more. Minus 85. So what's happening as we zoom in, we can't quite catch the minimum. It's shooting down to minus infinity. So you can't really see it on this graph, but what's happening is the shape of it. We have a maximum here, a maximum here. So it's like almost like 2 quadratics, but then they come together and they shoot down to minus infinity here. So we only have 2. Now, let's reset that. So you don't need to draw a graph this difficult in the exam. Okay, this is too difficult for the exam, but it is good to understand what these numbers mean. So our two answers, our first answer was here, so I can call that like A, and then our second one was here, we call that B. But I like this example because it shows you that because you have two turning points, you might think in your head, oh, if I have two turning points, then one turning point should be a maximum and then the other turning point should be a minimum. But this example I like because they're both maximums. This is a maximum at the top of a hill, and this one's also at the top of a hill. Okay. This will be more important later when we do, as you were saying earlier, the second derivative. Some people know what I mean. Yeah. What do we use this one for? The second derivative is used to decide if it's a max or a min. Okay. But anyways, for this lesson, all we're doing is using the first derivative to find the turning point. Okay. So let me tell you which ones to try here. Cubic. Number 10. It's the 10th one, actually, number 10. And then the last four. 25, 26, 27, 28. The last four. Okay, so you have 5 minutes, so you can start working on those for a few minutes, okay? And actually, if some people have questions about the assignment, if there's something they want me to check, I can do that now as you work, okay?